Welcome students. In today's class, we look at the concepts which are required uh, in order to understand the topic, that is relation between perceptron and the base classifier for a Gaussian environment. That is, in the class until now we looked at the perceptron, but we have to look at what is the relationship between the perceptron and the base classifier. To understand this thing, before proceeding further with this topic, we have to put some foundations to understand what is meant by Gaussian distribution and probability with respect to intersection and conditional probability, Bayes theorem and the Bayes error. If you are already familiar, you can skip this one, and then after discussing this one, then I'll start with this topic. But if you want to get familiarized, then you can continue. Now, Gaussian distribution. What is a Gaussian distribution? Gaussian distribution, also known as the normal distribution, is a continuous probability distribution characterized by its bell-shaped curve, and it is defined by two parameters, that is mu, which is the mean or expected value of the distribution, sigma, the standard deviation, which measures the spread of the distribution. The probability density function of the Gaussian distribution is given by the formula which is shown here, that is 1 divided by sigma standard deviation square root of 2 pi and exponential e. It is a Euler's number to the power of minus x minus mu, that is x is the input variable, and then mu, the mean whole square, divided by 2 sigma square. And here you are looking at a graph which is going to show to illustrate the concept of the Gaussian distribution. We will consider the distribution of the birth weights for the full-term babies in the large population. That is, when the baby is being born, the weights of that particular babies are being taken, and it is being plotted in the form of a graph, that is the Gaussian distribution. Now, when we plot, that is the birth weight with respect to the probability density function calculation, we can see the graph which is going to come like in a bell-shaped curve. What is the observations from this graph? What it does, that is, most babies' birth weights are clustered around the average. That is, the mean average is coming around 3.5 here if we take the center point here actually. That is, the birth rates are average, that is, baby births are clustered around this particular average value, that is peak of the curve actually. And fewer babies have birth weights that deviate significantly from the average, that is this thing. That is, very few babies have a extreme birth weights, that is very high, that is this one, are very low actually. But most of the weights of the births of the babies are clustered around the average. That is, if the patterns are Gaussian distributed or normal distribution is there, then the pattern values will be clustered around the mean of that particular pattern values actually. That is the input what we have to take from the Gaussian distribution. When we plot the Gaussian distribution for more than one variable, that is, here what you are seeing is a visualization of the three distinct one-dimensional Gaussian distribution. Here, this graph is for one variable actually. And then here what we are seeing is the Gaussian distribution for three different variable or three different patterns actually. What we can observe here is, that is, if the mu value is very high, or in the sense whether it is -5 here for this particular graph here, and mu value is, that is a average value is 5 for this graph, but the average value is 0 for this graph. But what is the other observation we can see is the sigma actually. That is, sigma decides the width of that particular curve. That is, for the blue curve which has been shown here actually, it is the sigma value is 1.2, which is very narrow. And then for the curve which is in the orange color here, the sigma is 1.8. So the values are spread across it. But for the curve which is here in the green color, the sigma value is 1.6. That is, it is medianly spread across. That is, when we take the variables with more than one in the patterns actually, and there will be some overlap occurring between the Gaussian distributions. That is what the observation what we have to look at here actually. And the sigma decides the spread of the values. Now, to understand further the Bayesian theorem and then the Bayesian error and the Bayesian risk, we will take one example where based on the tumor radius, uh, it is being decided whether that particular tumor radius uh, that is depending on the tumor radius value, whether the class is benign or malignant. That is to decide two class values depending on the two radius. It is just a hypothetical example actually to make us understand the concepts which we are going to discuss further actually. That is, depending on the tumor radius, that is the class values are being assigned actually. What it indicates, that is, if the tumor radius was around 10 mm or 11, 12, 13, 14, 15, it is being decided with the class benign. And then similarly for the other radius values 14, 16, 18, 19, 21 and 23, it has been decided as a malignant actually. Now for this particular two classes, when we calculate the average for the benign case, the average value is coming out as 12.5. And when we calculate the standard deviation, its value is 1.87. Similarly, for the malignant, it is 18.5, the mean value, and the standard deviation value is 3.27. Now, say if the tumor radius was 14 mm, what is the probability density if the tumor is going to belong to the, whether it is benign or malignant, we can calculate. But we are asking here the question, if the tumor radii was 14 mm, what that probability density if the tumor is for the benign case. At that time, we take this particular probability density function, and then this x value will become 14 actually. And now for the benign case, that is, we had a sigma value that is 1.87, and then the so average value what we had was 12.5, that is what we have fitted here actually. And now when we calculate for this particular benign this thing, we are asking just if the probability density of the tumor is benign, then its value comes out to be 0.154. Similarly, we can calculate for the I think for the malignant case actually, when we calculate, it is going to come out to the value that is 0.47 actually. But we will do some interpretation on this particular this thing actually. See, when we take 0.154 in the sense, like for the benign cases, the values are in the range of that is 10 to 15. But anyhow, there is some overlap here actually between the benign and the malignant actually. Therefore, with full confidence, we can not tell that the 14 mm radii is going to belong to the benign or not to the malignant. But here, what it is telling is, this is with respect to malignant, it is going to come to the 0.47. The value is very less because there are only small probability that it may belong to the malignant, but very high probability that it may belong to the benign case actually. Now, other interpretation is when we multiply this, that is, uh, this is 0.314 and we got 0.154 actually. This value what we are getting, that is 0.154, this is almost equivalent to the height of that particular curve. See, when you this is the x value, that is a radii. That is when we take, so we will take the value here, that is 0.154 may come here actually. And then when we plot it back, it comes around, that is 14 actually. That is this value what we calculate, which is equivalent to the height of that particular curve actually. Now, when we consider this x as 14 with respect to the malignant, yeah, the line is going to coincide here actually. That is, for that one, the value what we got was 0.047 actually. That is, you can observe 0.47, which is almost somewhere here actually, which is good. That is, this values when we calculate whether it for benign case or malignant case actually, the probability density function will give us the height of that particular curve where it is going to coincide. Now, to recollect, we will have to understand the probability concepts with respect to the intersection and the conditional, because the Bayes theorem is based on the conditional probability. Therefore, we'll understand this one with the example and then we'll proceed with the Bayes theorem. Now, we will take the same example actually, the benign and the malignant case actually. And then we will take two events. One event is tumor is malignant, and the other case where the radius is greater than 13 mm. That is, we'll just take these two events actually for the example actually. A event is tumor is malignant, event B is radius is greater than 13 mm. Now, the radius is greater than 13 mm are belonging to the tumor with the IDs, that is 5, 6. From here you can observe 5, 6 up to 12. That is how many tumor IDs are, how many instances will fall into this particular category. That is totally 1, 2, 3, 4, 5, 6, 7, 8 are going to fall into this particular category. Now, this big circle, the blue circle which you are seeing, is for the event where the tumor radii is greater than 30. Therefore, 5, 6, 7, 8, 9, 10, 11, 12 will fall in this particular basket. But what is the event A? Event A is a tumor is malignant. Therefore, this event is going to fit inside this particular circle, and 7, 8, 9, 10, 11, 12 will belong only to the malignant case, but also greater than 30. But 5, 6, which you observe here actually, the tumors with the IDs 5, 6 are not malignant. It is benign, but it is greater than 30. Therefore, it falls outside this particular circle. And then tumors with the tumors with the IDs 1, 2, 3, 4 are only belonging to the case of, that is the benign case. Therefore, 1, 2, 3, 4 are being written here actually. That is, from this slide, what is the summary we have to take is like how we have fitted the values depending on the event A and B in this scenario, and then drawn in the form of a Venn diagram to show the set values. Now, when I ask the question, what is the probability of A intersection B? What it is asking, whether that is tumor is malignant and its radii is greater than 30. Now, to understand this one, first we'll calculate what is the probability of it. That is, the tumor is only malignant. 6 instances are there for that particular given thing. Therefore, and total sample space is what? 12. Therefore, it becomes 6 divided by 12. And what is the probability of the event B actually? That is, the tumor is greater than 30. It becomes 8 by 12, because 8 in this, including this one, it becomes 2 plus 6, that is 8. Therefore, 8 divided by 12, which is going to come to the value 0.667. Now, A intersection B in the sense, what we are trying to ask actually, that is, if there is a slightly overlap, that is, this is the event A and this is the event B. We are asking what is the A intersection B we are trying to ask it. At that time, it will be the probability of that particular, that is, if I take this one, that is this one, that is the probability of the event A occurring with respect to the B divided by the total number of samples which are there in that particular this. Therefore, this comes out to be 6 divided by 12 because A and B together, how many we got? We got only the 6 actually. But the total samples is what? 12 actually. Therefore, it becomes 6 divided by 12. Now we will look at the question of, that is the understanding the concept of the conditional probability. That is a conditional probability. What it asks, what is the probability of the event A occurring given, that is B as occurred, and what is that the event A is going to occur. That is what we are asking. Now, to understand this one, say I will take the event A and then the event BH. And this is A intersection BH. Now, in this one, we are telling, let me draw different. That is, this event has occurred actually. That is the probability of the, that is the event B has been occurred actually. Now we are asking, if B has occurred, what is the probability that the A will occur? At that time, what it becomes? It becomes probability of A intersection B whole divided by probability of the BH. That is the thing. That is, whenever we have to calculate the conditional probability, that is probability of event A occurring given B has occurred, it will be the probability of A intersection B whole divided by probability of the BH. Now, for this particular example, that is the tumor radii example actually, it becomes the value of, that is probability of A intersection B is 0.55, and then probability of the B value what we got is 0.667 actually, and it is going to come to the value that is 75. That is what it indicates. It is 75%. That is, if the tumor that is whether the tumor is malignant given the radii is greater than 13 mm, is we are telling with the probability as 75%. That is the thing. Now we will proceed with the Bayes theorem. What the Bayes theorem tells actually, that is, a Bayes theorem is calculated with, that is calculation of the posterior probability, that is probability of event A occurring given B has occurred. It is the evidence, whether that is the complete probability of the event B, and then the numerator will be with respect to the multiplication of the likelihood with the prior probability. That is a likelihood probability. What is the probability of the B occurring given A has occurred, multiplication with the prior, that is the event A has occurred. Now, when we relate this Bayes theorem formula with respect to the class and the features, that is given the features, that is in this example, that is the radii is being given to us, and we have to decide whether it is benign or malignant. Then what it is asking actually, the Bayes theorem, it is a probability of the class, that is the prior probability, and then conditional probability, probability of the features with respect to the class, and then divided by probability of the features actually, that is the evidence which has been occurred. Now in this example, that is we will take the feature as the tumor radius, that is the X actually. Our classes are two, that is the malignant and then the benign case actually. We can call benign case as class 1 and malignant as class 2. Posterior probability, what we want actually. That is, what is the probability that given some radii value of the X feature, that this as is being given, then how we can decide whether it is, with what confidence we can decide it is a malignant. That is, a probability tumor is malignant after seeing the radius X. Likelihood, that is P of X given malignant. If the tumor were malignant, how likely is this radius? That is, if we tell it is a malignant, how likely this radius is going to belong to the malignant case. Prior probability of the malignant. Before seeing the radius, what is the chance of malignancy? Evidence is the overall probability of the feature. That is overall probability of seeing this radius in the population. It will be calculated with the probability of X given malignant. That is this one to understand. That is, when we take our whole sample space will fit either in the malignancy case or benign case. That is, X is a feature value which is the radius. Either this radius has to fit in this malignant case or the benign case. Now some X value has been occurred actually, and we have to find out like uh, whether with what ratio that this belongs to this and this one. This is when we have to calculate. We can also calculate this as, that is, it is probability of X intersection malignant plus probability of X intersection benign that we can do. Now, previously we have seen, that is, whenever we have to calculate, that is X given malignancy actually, we can write it as probability of X intersection malignancy divided by probability of the malignancy. Therefore, this X intersection malignancy, we can write it as probability of X given malignancy multiplied by the prior probability, that is probability of the malignant. Similarly, we can write it for the benign case. That is, this evidence is nothing but the total probability of that particular event. Therefore, it combines from both the classes, because here two classes are there. Therefore, we are combining it with respect to the both the classes. Now, when we have to decide, given the X actually, we have to calculate the posterior probability for both the classes, that is a malignant case and the benign case. Now, as per the Bayes theorem, that is, this is the likelihood probability, and this is the prior probability, and this is the total probability. Now we will calculate this value and find out what is the values that we get with respect to the malignant case and the benign case. That calculation, I will show it here. Yeah, with respect to this one. That is, our aim is we have to do the calculation for this two things actually. Therefore, we'll go with the first, this one. That is, from the given population actually, 6 are belonging to the benign case and 6 are belonging to the malignant case. Therefore, a priori we can decide it as probability of malignant is 6 divided by 12. Similarly for the benign. Therefore, it becomes 0.5 for both the cases. And now previously we calculated this probability of the radius 14 belonging to the class benign, which was 0.154. Similarly, for the malignant case, we got it as 0.047. Now, when we have to calculate the numerator value for the Bayes theorem, then this value, that is probability of 14, conditional probability of 14 with respect to malignant multiplied probability of the malignant, which is going to become 0.047 multiplied by 0.5, which is going to come to the value that is 0.0235 actually. And now the total probability actually, that is, this is this with respect to this one actually, which is going to come, that is X given for this case actually, malignant case, which was 0.047 multiplied by 0.5. Similarly, this was for the benign case, which we got it here actually, and then 0.5. Now when we evaluate, this is going to come to the value 0.1005. Therefore, now for the probability of the malignant with respect to the 14, it will be, that is the total value what we got for this particular numerator, it was 0.0235, and then this evidence value, that is 0.105, which is going to come to the value that is 0.234 actually. And similarly, we can calculate the benign, that is probability of the benign with respect to 14 using the formula. But anyhow, we know we only two classes are there. When we have calculated the probability for one class, the other class we can calculate it as 1 minus the probability of that class, therefore 0.234, which is going to come to the value 0.766. That is now finally probability of the malignant with respect to the 14. That is, we are asking the question, if the radii X is 14, what is the probability that it may belong to the class malignant? Similarly, we are asking the question, if my tumor radii is 14, what is the probability that it may belong to the benign class? That is, more chances are there. If the tumor radii is very less, it may belong to the benign case, because we can see in the sample space here actually. That is, for the smaller radii values are belonging to the benign case. Only for larger values are belonging to the malignant case. But there is anyhow some overlap is there. But the chances of belonging, that is, if the tumor radii is 14, what are the chances that it may belong to the benign case or malignant? Now, as per the Bayes theorem, when we apply it, we are getting this one. Now, what is the conclusion we can draw? That is, when we have two classes, that is C1 and then the C2, we are going to calculate the posterior probability of that particular class with respect to the feature, that is P of C1 with respect to the X and then P of C2 with respect to the X. Now, in case if posterior probability with respect to the class C1 is greater than C2, then we will tell this feature X belongs to the class C1. Else, if this condition does not satisfy, then we will tell the feature, the input feature X is going to belong to the class C2. That is what this thing. That is, in the Bayes classifier, we are going to calculate the posterior probability of the given feature with respect to the class and then find out what is the values we are going to get with respect to each class. If one class value probability is greater than the other class, then we will decide that as a X. That is, a new input feature X will belong to the class C1. Now, we will understand the Bayes decision boundary. What the Bayes decision boundary tells is the optimal separating surface between the classes that minimizes the total probability of the misclassification, because any classifier should give us very less misclassification, that is the expected loss. With respect to the Bayes classifier, it occurs where the posterior probability of the two classes are equal, or where the ratio of their conditional densities matches the ratio of their prior probabilities. That is, earlier, that is, when you take this particular Gaussian distribution of the benign case and then similarly the Gaussian distribution for the malignant case, and then when we plot the graph, actually it is going to look like this depending on the average and the standard deviation, mean and the standard deviation. That is, whatever the patterns we draw for the classification, there will be some overlap. That is, there is an overlap here actually. Now, obviously, if there is an overlap, what is a point we can draw actually? If there is an overlap, there will be some portion of misclassification for sure. That is, a classifier system will do the misclassification for sure. It is unavoidable actually, because we cannot have a patterns which are totally independent. There will be overlapping patterns will be there for sure actually. Got it. Now, to proceed further, now to calculate what is a Bayes decision boundary, that is, this thing I told, we can calculate the posterior probability of the features and then decide whether which one is greater than and which one is the other thing. But can we have some constant value which is going to tell, that is, what decision boundary we can calculate, tell whether this belongs to the class 1 and other belongs to the class 2. Obviously, when we see this particular Gaussian distribution, wherever there is an overlap, that is, you can observe in this particular this thing, that is, overlap is occurring for sure here. This is a point where our posterior probabilities of the two classes will become equal for sure because this is a point we can decide whether it can be a benign case or a malignant case actually. It can be anything arbitrary actually. Therefore, now we want to know what is this value for the X-ray, that is a X feature value. What is that value? What we want to know actually. Now when we want to know that one, we can equate the probability density function for both the classes actually. That is for the benign case and in the malignant case actually. That is, this is the probability density function with respect to the malignant case, and similarly the probability density function with respect to the benign case, because this y-axis is a probability density function. At this point both values are becoming equal. Now when we apply the values and then when we solve this particular equality for the x value, we are going to get the x value as 15.22 mm. What is the conclusion we are trying to draw by calculating that 15.22 actually? Because this point is where the decision is going to happen actually in the base class. That is, if the x naught value, if any x naught value, that is the input feature, that is input feature value is less than 15.2 mm, we are going to decide it as a benign case actually. But whenever the input feature value, if it is greater than x, we are going to decide that as a malignant case. That is, this becomes the decision boundary. How we made the decision boundary? That is, we equated the probability density function value of the benign case and then the malignant case actually. And then we got this particular this thing. Now, if we know this particular decision boundary, whenever the new feature comes into the classifier, you check whether the x value is less than the decision boundary or the x value is greater than. If the x value is greater than the decision boundary value, decide it as a malignant. Or if the x value is less than the decision boundary value, then you decide it as a benign case. But there is a problem with this one actually. The problem is, okay, this one. That is, this curve is for the class 1. We'll call it as a benign case actually. This is a benign case curve. When we got the decision boundary value, we are telling if it is x is less than 15.22, you decide it as a class that is benign. Now, this curve, that is the orange color curve which you are seeing here actually, this one, that is this blue curve, this portion is actually for the malignant case actually. But here we are trying to decide that as a benign case actually, which is an error. Similarly, now the other portion actually, when we take this side actually, here, this portion was belonging to the benign case, but as we are moving x greater than 15.22 and we are deciding the class as a malignant actually. That is here, left shaded area under the malignant curve. That is, malignant tumors are misclassified as benign because x was less than 15.22 and we are deciding it as a benign actually. That is, actually it is a malignant tumor, but we are deciding it as a benign case. Right side, what is happening? We are deciding it as a malignant, but it is actually what a benign actually. That is, benign tumors are misclassified as malignant. What we're trying to make a conclusion is, whenever we take the input feature patterns actually and draw the Gaussian distribution, there will be some overlap occurring. If the overlap occurs, for sure there will be a misclassification and also the error will occur for sure. This is unavoidable in any classifier. We cannot get, if there is an overlap in the patterns, there will be an error for sure. First, some percentage of error will be there in the classifier for sure, which is unavoidable. But only thing is, can we minimize this error? That is what we are going to ask the question. That is how much we can minimize this particular error. Now, to look at this particular minimization of the error, we will look at how we can quantify this particular error actually. That is, this portion is our error now actually. How we can quantify? The error we can quantify by taking the integral, that is integral here is from minus infinity to the decision boundary value, that is x naught, and then multiplication, that is integrating over the posterior probability are equivalent to that particular density, probability density function actually. And we have taken this as that is the likelihood function multiplied by the prior probability and then integrated over the x, because x is the input feature, that is this is the x actually. That is, this is with respect to the one case until the x star, and this is for the other case. Therefore, integration happens from x star to the infinity. Now, in our example, our decision boundary was 15.22 actually. Therefore, the probability of error modeling will be from minus infinity to 15.22 with respect to the malignant, because this portion, we are deciding it as benign, but it is actually what? A malignant case actually. And this side, we are deciding it as malignant, but it is benign case actually. Therefore, here it is an integral from 15.22 to the infinity, and probability density, that is likelihood probability P of x with benign, and then 0.5, because we got in this case 0.5 the prior probability. That is, takeaway from this slide is to model the error actually, we are going to look at how much the error. It is an integral of, that is from this side, we are deciding it as benign, but it is actually the malignant. Therefore, we are going to take with respect to the malignant probabilities here actually. And this side, we are deciding it as a malignant, but it is actually the benign actually. Therefore, we are going to take the integration this side actually from the 15.2 mm to this particular point. Now, our aim is we have to reduce this particular thing. Now, we'll look at how we can reduce, because later I'll tell why we are looking to this one and how we can shift this particular boundary. Now, you introduce one term that is called the cost, because our aim is we have to reduce this particular error. Whether we can shift this particular boundaries, whether to the left or to the right, so that we can reduce the error. For that, we will take the term CIG. CIG is cost of deciding the class I when the true class is J. That is, we are deciding the class label as I, but actually the truth is J. That is, here, as I said, if x is less than x naught, we are deciding it as benign. That's fine. But there is an overlap here actually. This actually portion belong to the malignant case actually. That is, we are deciding it as benign, but it is a malignant. That is what we are doing. Now, when we take this particular cost, Cij actually, there are two classes actually. Therefore, the cost matrix will contain four values. That is, one is we are deciding it as a benign and whether the true is benign. And when we are deciding it as a malignant and the true is benign. That is, here you can observe C11. We are deciding it as class 1 and true is 1. When we take C21, we are deciding, that is a prediction is class 2, but actually it is the class 1. Similarly, we get for the malignant distinct. Now, when you observe this one, that is C11 and C22 are the correct classification, because we are deciding it as 1 and the true is 1. Similarly, C22, we are deciding it as 2 and but actually is 2. Therefore, we can take the cost of this particular correct classification as 0, because that is not going to incur any error. Now, to make you understand clearly, let me now erase this particular portion actually. Now, let me draw where that C11 is going to come. That is, this portion is the correct classification which is happening, that is C11 here. And the other portion, this side, this portion is C2 to actually where the correct classification is occurring. Now we'll go with the other terms actually. Now C12, that is C12, that is C1 is class 1 is benign and C2 is malignant case. C12, what it does? We are deciding it as benign, but actually is a malignant. What I said, that is in the decision boundary, if x is less than x naught, we are deciding it as benign, which is class 1. Therefore, C12 is going to come in this portion. We are deciding it as benign, but actually it is a malignant. Now, similarly, the other one, that is, if x is greater than x naught, we are deciding it as malignant, but that is C2, but actually it is a benign. That is this portion, that is C2-1 actually. This is the portion actually. That is in the graph, you should look at where the cost matrix values are going to get plotted on the graph, where the C11, C22 and C12 and C21 is going to come. Now for us, the penalty or the error is with respect to the C12 and then the C21 actually. If we associate equal penalty for this one, that is both errors are equal, then it becomes the value 1, 1 here. Any value we can decide, but for the error, there should be a penalty associated actually. Here we have decided it as, taken it as 1, 1. For correct classification, it does not matter. Therefore, the cost or the penalty will become 0. Now, here, same thing, that is C11 and C22 is 0 and C12 and C21 are 1 actually. That is, this is the error, any mistake counts equal as 1 error. But here, we have to question ourselves actually. I'll just put it back, that is, this was C11 because this was the case of C11 and the benign. And the other terms I'll just put it because here we have to question ourselves. One, this was C2 and it is a malignant case, and this was C2 to it. Now x was less than x naught, we are deciding it as benign, and x greater than x naught, we are deciding it as malignant. Now we will put one question. See, when we have to screen a large population for any disease, whether it is a cancer or anything actually, what we will do, we will take this large population people actually, we'll do some initial screening. Initial screening will be done actually to find out whether there is a disease in the population or not, the human being population or not. Usually this can be a mammography or an MRI, something like that. MRI will not be done because it is costly. The initial screening where the cost is very less, that will be done. Let's say mammogram is being done actually, something. Now, when the large population was around 1000, we will do the initial screening and reduce it to 100. That is a suspicious cases, or whether we have to do further follow-up or not. In case of cancerous, what the system will do actually, in the thing is, this 100 which is being filtered from 1000, this samples will be sent for the biopsy actually. Biopsy in the sense that is taking the cell and then testing whether actually it is a cancerous or a non-cancerous. Because initially for 1000 we don't have to do this biopsy because we can filter and then further make a final decision whether it is cancerous or non-cancerous. Now the question is, like this error what we are doing, let me erase this one, because we are doing some error in this particular thing. Which error is appropriate and which error is not, both errors are not appropriate, but what may be the cost associated. See, say when we take the true class was malignant, but we are deciding as benign. Other way around, if the true class was benign and we are deciding it as malignant. What I'm trying to tell here is, that is, will take, we are doing some initial screening of the population. It was around 1000. And then after doing the initial screening, we are bringing it to 100 actually. See, when we have brought this to 100, further we told we will send this to biopsy and figure out whether it is further cancerous or non-cancerous. That decision we will take. Now, when we did the initial screening and then we decided actually it was malignant actually. It that is a prediction by the classifier assume it was decided as a malignant, but final call was not being taken. Therefore, these cases will be sent to biopsy and then finally we can take a decision as it true class is benign and we are going to decide it as a non-cancer. That is, uh, when the decision was malignant but the true was benign, it is fine because further we will do the biopsy and then we will make a decision. But you look at the other error, what we are trying to do actually. When we did the initial screening actually, we are deciding it as a benign actually, but it actually a malignant. Then these cases will not be sent for the biopsy. But actually the case was what? The true was malignant. We should not miss this one. That is this class we should not miss actually because this is a serious case because the patient was suffering from some disease actually. But when we did the initial screening, we are telling there is no disease. Then we will not do the further follow-up of such patients and then we'll miss this one. This has a serious consequence actually. That is here, in this particular Gaussian distribution, this is what we are deciding it as a class 1, but it is actually class 2 actually. That is C12, where we are deciding it as a malignant, we are deciding it as a benign, but actually it is a malignant actually. That is, this error we should try to minimize as much as possible. Because this side is what? We are deciding it as malignant, but it is actually a benign. But this, if you have decided at the initial screening as a malignant, later we can do the biopsy and we can make a final call. But if you have decided as a benign, but it is actually a malignant, then we will miss such cases. We should not miss. Now we have to look whether we can shift this boundary towards this side so that we can minimize the errors further actually. That is what the question we are going to ask. Hope you have understood what we are trying to figure out, like how we can minimize this particular this thing. Therefore, that is what we are trying to come with this thing is, the conclusion is, if the benign tumors are classified as malignant, that is fine because further follow-up will do and then make a decision. But malignant tumors should not be classified as benign actually, because this is a serious consequence which we should not miss actually. Therefore, here when we take, that is, this was C12 and this was C21. Therefore, the penalty for the C12 should be more actually. That is 10 or greater than the C21 actually. Therefore, we have assigned it as 10. It is no hard rule whether why it is 10. It can be 2, 3 or 4, but greater than this one. But penalty for this C21 may be lesser actually. Therefore, we can consider this as 1 actually. That is the thing. That is, now missing a malignant tumor costs 10 actually, because that we should not do. And this particular C21, it's okay. 1 we can take. That is, I'm trying to make you like why the penalty for the C12 should be greater when compared to the penalty for the C21. Now, the last term, what we have to understand here is base risk. Base risk is the minimum expected loss of the decision rule calculated by averaging the loss function over the posterior distribution of parameters representing the best possible performance achievable in a Bayesian framework for a given problem and then the loss function. That is the what is the overall achievable this thing we can get from the Bayes framework, or what is the total minimum expected loss we can get at. That is, our thing is, this was the correct classification, this areas, but this was the error classification. But now we have to look at what is the overall expected loss based on this particular decision. Now we'll write the formula for the risk actually. That is the R actually. Now when we have to do, first we have to take this correct classification, that is C11, and this is an integration with respect to the area R1, because this one is there. We are trying to model the risk actually, that is R1. This will be with respect to the, that is we are in this area where we are with respect to the C1 and then the integration, therefore dx, and this will be with respect to the P1, that is P1. Now similarly, that is we will go with the correct classification, that is C22, and then this integration, this side it comes, this is C22 and this was C11 actually. Therefore this comes with P of x with respect to the C2 and then dx, and the prior probabilities, that is P2 with respect to this one, but the area was, that is R2 here in this particular sorry, 1 minute. 1 minute, students. I made a mistake actually. Let me erase this one. This is correct actually. I slightly made mistake. I'll correct myself. One. That is, now this was x. This now we will go with modeling this C12 actually. That is C12 will multiply. We are in the region R1, but this is with respect to, that is Px and then C2. What does it mean? Why we have written C2? Because we are deciding it as class 1 actually, because x is less than x0, but it is actually what? For the class 2. That is the malignant area curve coming under the benign case actually. Therefore, getting multiplied with the prior probability of the 2 and then dx. Now, plus C21 we will take. That is this side, C21 actually. That is, we are in the region now 2 actually, but this side we are deciding it as 2, but it is actually the class 1 actually. Therefore, it is Px of C1 and then dx. Therefore, multiply with the prior probability of the 1 actually. And then this is C22, that is this side. And then it is integral over the R2 and then P of x with respect to the class 2 dx and then P2 actually. I'll make you familiar once again with this formula, because this is what the base which we are going to use it for all further. Got it? That is C11 is this one with respect to the region 1. We are deciding it as 1, but actually it is the class 1 C1. Therefore, it is C1 here and then the P1 here actually. And then the next term actually. That is the next term is we are this C1 2 actually. We are in the region, sorry, we are, I think I will take the other color. We are in the region R1 actually, that is this particular region only, and but we are deciding it as C2, therefore it is C2 here actually, which is going to come here actually. And then the next term, because this one is one which is required for all further this thing, C21, we are deciding it as 2, but it is actually the 1 actually, this side actually, because it is x greater than x naught actually. This is for the C2 and this is for the C1 actually. Therefore, it is an integration of this 1 actually, therefore 1 here, this one, but we are in the region R2 here actually. And similarly, C2 to this side, that is integration of R2, that is sorry, integral over the R2 in the region R2, but with the class that is 2, but with the prior probability that is the P2 actually. Hope you have understood this particular, how we are drawing this particular risk equation by looking at the graph. Now, finally, this is this thing, that is C11 here, and then it is integral over the region R1 actually, and then here the C2 to this one, and it is integral over the region R2, and then C21, that is C21 here actually, and it is integral over the R2, this region, and then next it is C12, that is it is an integral over this particular R1 region actually, R1 region, but with respect to the class 2 actually. Now in this one, if I put C11 and C22 as 0, this is the correct classification actually. Then this terms are going to get invalidated, C11 and then C22 actually. And then if we take C21 as 10, that is this one here actually, C21 as 10, and then C12 as 1 actually, which is going to get simplified to this one. Now, the final risk is only with respect to this particular two terms actually, which is going to. Okay.